Hello and welcome to episode 149 of the eBPF and Cilium office hours live stream. So today, first things first, as always, if you're watching live, do say hello. I'm also going to let you know that we're experimenting with a different streaming platform today. So I also want to hear if you notice any differences in quality, any differences in the sound, anything like that. Do let us know. As always, say hello, let us know where you're watching from. It's always great to hear from you. Okay, so in episode 149, we are going to mostly be talking about Tetragon with my guest, Kev Sheldrake. But before we get to that, couple of events I wanted to make sure you're all aware about. So you may well know that the schedule for KubeCon has been announced this week. And I just took a quick look to see how many things are talking about eBPF. There are quite a few interesting sessions in Salt Lake City at KubeCon about Cilium and eBPF. As always, if you're going to be there, we'd love to see you. Do come and say hello. There is also going to be a co-located event for Cilium and eBPF Day. So that's going to happen on the day before the conference starts. The schedule for that's going to be announced, I think, any day now. Another event where the schedule will be announced any day now is eBPF Summit 2024, which is coming up in less than a month's time. Speaker notifications have been sent out, and we will be announcing the schedule very soon. So really excited about that. That's going to be another, 4 to 5 hours of incredibly insightful eBPF related content. So I'm very much looking forward to that. And I hope you will join us. Go check out the link in the show notes, which you'll find there, hackmd.io under eCHO Live. You'll find the show notes for episode 149, and there is a link there to the registration page for eBPF Summit, or you'll just find it from eBPF.io, I'm sure. Okay, with that said, I think it is time to introduce my guest for today, Kev Sheldrake. So, hi Kev, welcome to eCHO again.
Hello again. How are you doing?
Good, yes. So you've been working on Tetragon for, quite a long time now. So today I think we're going to not just do like a beginner's intro, we're going to dive into a few tips and tricks and surprising things that maybe not everybody knows about Tetragon.
Well, exactly, yeah.
Hello from Piotr in Poland. So thanks for saying hello.
Hello to Poland. Yeah, I mean, I'd say I've been working on Tetragon for probably over 2.5 years now. A lot's changed in that time. I mean, we open sourced Tetragon in that time. And there's a lot of features that get added at quite a rate. And obviously, it's difficult to keep up with exactly what new features there are. So, yeah, the idea of just showing off a few of the things that people aren't that aware of seems like a good idea. If I share my screen,
let me turn that on. There we go.
Then hopefully I'll be able to show some of the things. So one of the things I wanted to show were network selectors. So TCP/IP stack kind of selectors. So things that we can make decisions on. So obviously with Tetragon, you can hook pretty much anywhere in the kernel. You can make decisions based on the data that's coming into functions, different function arguments. And based on those decisions, you can then send events or not send events, etc., etc. Well,
we should probably, just in case there's anybody who hasn't come across Tetragon before, we should probably just quickly say, yeah, it's an open source project, part of Cilium, and it's typically being used for security observability and also security enforcement. So we're using eBPF to hook into these events, filter out, so we're only looking at the interesting events that maybe are malicious or suspicious in some way, and then we're doing something to let users know or to react to those events, right?
Exactly, and there's two kind of distinguishing features of Tetragon that sets it sort of aside from pretty much everything else in the space. So one of those things is that most tools that are used in eBPF, they've predetermined where they want to hook, what they want to monitor, what they want to capture, and then you might be able to configure it a little bit beyond that. But if you wanted to hook somewhere differently, or if there was a new threat that you could counter by hooking somewhere, you generally have to wait for them to kind of update their hooks before you can get any advantage of that. Whereas with Tetragon, you can hook pretty much anywhere you like. So if a new threat came along that involved you hooking somewhere new, you just need to find that function and then hook it. So that's one thing that's kind of different. The other one is typically a lot of the products in this or solutions in this kind of market space, they capture all the information at those hook points, and then they send it to user space, and then in user space they filter it. So you don't send all of it out to your SIEM or whatever. But also, you can collect a few different things together, and together they might form an event in their own right. Well, with Tetragon, we do a lot of that filtering in the kernel, so in eBPF. So we capture the information in the kernel, and then we analyze it, and then we make decisions at that point, which means that we send a lot fewer events to user space, because all of those ones that you're just not going to send out to your SIEM, we don't send it at all. And a lot of the joining together of different events is something that, because the way we've written our programs in eBPF, we can actually collect together data from all of the different hooks and make those decisions in the kernel itself. So it's kind of more efficient. It lets you do more, and it's more efficient in the way it does things, which it's kind of exciting. I'm sure other tools can do different things, and obviously there's trade-offs to be. But if the thing you wanted was low overhead and ultimate observability, then Tetragon really is the one that I think is winning in that space. But
and I think there's a nice blog post about sort of benchmarking performance. So I'll try and find that and add the link to the show notes, because I recall it saying, I mean, obviously it depends what you're filtering, but it was something like under 2% CPU overhead for observing all the file read events that happen while you're building the kernel.
Yeah, exactly. It's remarkable. It's good. Yeah.
I think anybody would take a security tool that can be comprehensive with less than 2% CPU overhead. That's an astonishingly low amount.
Exactly. So let's have a look at some network stuff. So I've got some. In fact, we'll do it. I have some policies here. So I have one here called TCP. And basically what this is monitoring is all of your TCP connects and accepts, which is a very, unclose, because you want to know when a connection is made and when a connection closes. So the reason I mention this, lots of people who come onto the eBPF Slack in the Tetragon channel ask about network and observing network, and they usually start with our examples, which is where this kind of comes from. But then they have questions about how you join those examples together, or how could you extend them to do the thing that they're actually after. So I just wanted to talk a bit about that. What you'll notice first, of course, is I have these two calls here, skalloc and sk3, which do the magic socket tracking, so track sock or untracked sock. So every time we create a socket in the kernel, we track it, assuming that it matches our demands, which are that it's IPv4 or IPv6. We don't care about Unix sockets or other protocols in this particular example. And then again, on a socket 3, we untrack it. And what socket tracking is doing is it's tying the process that created the socket to the socket, so that later on when we report things about the socket, we can put the right process in the event. So the
event's going to contain all the information we've collected about the context of that event, and the process being an important part of that context.
Exactly, right. And so for a lot of other tools in this market who are monitoring kind of syscalls or very sort of towards the app layer of the stack, this is really easy, because in eBPF, you're running in the context of the process. You can get the process ID, you can use that to annotate your events. But with networking, you're not always running in the context of the process. If like a TCP connection can be closed because the other end sends you a FIN. When that FIN is received, the kernel is in the context of whatever the kernel is in the context of, and if it handles that FIN, it will just handle it on the socket. Well, so we want to capture, and the same would go with the accepting the connection. When that SYN packet comes in, the kernel's doing whatever the kernel's doing.
It's handling a network packet. It's not in the context of a user space process. Yeah.
Exactly. So what this will do is this will add that process to the event. So other calls that we're hooking in here, TCP connect makes perfect sense. But we're going to, I'll say we've got connect, we've got accept, we've got a second part of accept here, which captures the new socket that gets created as part of to handle the connection, and it maps the same kind of process onto that as well. So the whole thing's kind of transitive. So once you've got the socket tracking working, everything in that stack should get annotated with the right process. And a bit further on, we'll have close as well, TCP close. But what I want to show is I've annotated these, the connect and the accept and the close with some selectors here, and we're matching on the not data operator of index 0. So index 0 is argument 0, which is a sock. So TCP connect takes a struct sock, which is a kernel structure, which represents a socket. And we can match on that with all sorts of operators. So normally you'd have operators like equals or in a map, in a list, not in a list, maybe less than, greater than, those kind of things. But because we've got a socket, we've got so much more information. So we've got things like source address, destination address, source port, destination port. So
data being destination address, right?
Exactly. And not data meaning not any of these. Okay. So if the destination address is not in any of these subnets, and we can take IPv6 subnets as well and individual IP addresses, it's not just CIDRs, then this will generate an event. So what we've kind of created here is a policy where we want to know about all the connections that are leaving and going to the internet. And we're trying to and we're not caring about local connections on loopback or local addresses. So, maybe you're quite happy with your clusters communications between all the different pods, but maybe what you care about is connections with the internet, either in or outbound. Catch those wily hackers with their reverse shells and the likes. So this would only report connects, accepts, closes, etc. that are remote, which is kind of cool. And I can quickly demonstrate that by running Tetragon with the right policy. Already running. That's not good. 1 second. I thought we were all set up. This is the standard.
No problem. While you figure out what's happening there, I'm going to try and answer a question because we've had a couple of questions came in that were really related to our discussion before about CPU overhead. And this question from Ashok, where he's saying, what's the impact on the CPU if we have more work happening at the kernel because these tasks have higher priority compared to a task from user space? And I guess really what we need to think about here is that application tasks, run in user space. They call the kernel for help using system calls, but there's no real concept, and Kev, correct me if I'm wrong, but I don't believe there's a concept of a task within the kernel. The kernel is kind of almost like a big monolith handling these, event-driven requests from either from user space or from some kind of device driver, like a network packet arriving. So the amount of work that's happening in the kernel really depends on what's happening in user space applications and what's happening in the device drivers that kernel's talking to, right?
Yeah, and we are adding some work because obviously we've attached to a hook and then we're running some code at that point. Obviously we try and minimize the amount of stuff that's possibly running, and when you measure your performance from user space, you're taking into account all of that extra work when you're looking at throughput. So if you measure performance, you're kind of accounting for it anyway. But if you're measuring, user space task type usage, then like with something like top or HTOP, then you wouldn't see the BPF burden. You can measure it by C group, I believe. But you need to revert to the blog post, and if the blog post is missing obvious information or use cases, then we should extend the blog post and make sure we cover those.
Meanwhile, I think you got Tetragon running with that.
Yes. I just had a different version of Tetragon running elsewhere for a test I was doing yesterday. Right, so that's running. What should we do? So if we asked for a web page from a local machine, we get a web page. Hopefully that's not giving away anything secret. And if we were to look for that, we'll find there's no events. So if we grep for TCP Connect, there's no event. No event's been sort of pushed in there. But if we were to do the exact same thing, and it's time go outside onto the internet, look for Google, then now we'll see we have an event. And if we were to pop that through JQ, we can see that we have kprobe is curl to Google, as we'd expect. We've got its parent, which is bash, obviously, and then we have the actual kprobe information here. So there's the TCP Connect function call, what we're hooking, and it's coming from my local IP address and going to one of Google's IPs on port 80 in state of sin-send. So the point of this sort of demo and talking about this sort of policy, and if I bring that policy back up, where here I was just trying to avoid logging packets or connections for traffic that I kind of trusted. It's just to give you an indication of the sort of things you could do. What you can do is you can add extra match args or extra selectors in here and have a number of different cases that you might care about, that you might want to match on. You can have any number of IP addresses in here. Obviously, we can have this is the not data version. You can have the data version. You can add extra matches for things like ports and combine a whole load of things. So if there's very specific traffic that you wanted to monitor, you could, and you don't want any other events, you could clearly do that. Or equally, if you want to just remove something that's very noisy out of your events, again, you could do that. And as I say, because these are being compared in the kernel and not in user space, then you save the CPU overhead of trying to process all those events in user space. And it's always cheaper to filter in the kernel. So that's what I wanted to talk about there. So network selectors, there are network selectors. So a second thing, which I found exciting, something that I added that I wanted, something I needed, is canaries. Now, not everyone knows about canaries, so we should talk about canaries. So from the days of the coal mine, apparently you would take a canary in a cage in the coal mine, and if the canary dies while you're down there, that probably means that there's poisonous gas in the air and you probably want to leave, on the basis that you could probably cope with it longer than the canary could, I presume, due to the capacity of your lungs. I don't know. Yeah. I don't even know if that's a real story.
It is a real story, but you're right. You'd think it would be about the concentration, but maybe canaries are particularly sensitive to whatever this poison gas is that comes out of mines. Yeah.
I don't know. Maybe the canary was just a good luck charm. But the idea, the concept of the canary being the first warning is the thing. So inside Linux, we've had stack canaries. I mean, they're in all operating systems these days, but we've had them for years. And a stack canary is a randomized value that's put on the stack that the program knows, but an attacker wouldn't know and shouldn't be able to guess. So it might be a 64-bit number that would be quite hard to guess. And the idea being that if you run a very old school buffer overflow kind of attack, and it overflowed the stack, and you were overflowing it to get to the return address, so you could control execution and get it to run your shell code, then you'd overwrite the canary in the process, and you wouldn't know what value to put in there. And so on return, the program would notice that the canary was wrong and therefore kill your process and say that's a bad idea. So and they're really popular and they're really good, and they defeat an entire class of overwritten return or controlling a return pointer kind of attacks, which no one does anymore because of stack clearance. Well, a company called Thinkst took the idea of canaries to the nth degree, and what they made were canaries that you can put anywhere, and if an attacker trips on your canary, you would get an alert. And so I want to kind of show, it's easier to understand it if you see it, so I want to kind of show it. So if we start off by going to canarytokens.org, which are free canary tokens, you can have as many as you like apparently.
I'm going to put that link in the show notes as well.
Excellent. So there's lots of different types, and it's worth looking into what all these different types are and how they work, because they all do the same job but in a different way. But it means lots of different places you could spot an attacker. So most of them are aimed for like a desktop. So there's Word documents, Excel documents, and things like that, which you just name it as like passwords.xls. You know, if you're an attacker and you see passwords.xls on someone's desktop, you're probably going to open that. But when you open it, the JavaScript or VB script inside it is going to run, and it's going to trigger a canary, and you as the system administrator are going to know immediately that someone's opened something they shouldn't have opened. So equally, it's like AWS keys, there'll be database stuff, there'll be all my Kubernetes when someone uses your kube config. I mean, isn't that a great idea? So
like a honeypot almost, right, for an attacker to see this
micro
thing. That's something.
Yeah, like super micro honeypots that you can litter them everywhere. So one of the things you can create is a web bug, which basically gives you a URL, and you can put that URL somewhere. So you might put that in a document. You might put it as a shortcut on your desktop, and then an attacker opens that URL, boom, it's triggered a canary. Well, with the free canary tokens, what it does is it emails you. But if you talk to Thinkst, they have a whole nother service which can send messages to your Slack, SMS to your phone, you know, all I mean, you name it, apart from fax, it'll probably do it, you know. But the email one is good enough to be able to demonstrate, and is good enough for a free solution, really. So if we put in an email address, kev.tetragon.canary. Obviously, it's not the email address I use every day, so please don't send me any emails. And then we give it a thing. We just say, no, it's a canary. For all that matters, it's just whatever you want to have in your message. And we create the token. It gives us a URL, and that URL looks very much like a web app URL for posting stuff. It's the sort of thing that an attacker might want to go, oh, I wonder what you can do. Do you need to be logged in? Are you already logged in? You can change anything you like between this slash and this slash. So you could have, you know, I love Kev in there or whatever you want, and it's all still work. It's basically it's I don't know. There's rules on it, but it's very clever. It's quite manipulative. So if we take a copy of that, and then all we need to do is put that into our policy. So which policy are we going to use? We'll use the one we just used. Remember where it is. What we want to do is say on a connect, if it matches this thing, instead of sending an event to our seam, instead let's have it trigger the canary. So we would put in here match actions, and we'd have an action which would be get URL, and we would have a arg_url, which will be our URL. I think it's probably enough. So we'll save that. We'll kill Tetragon and start it back up. See if it starts. Doesn't like it. I've done something wrong. Should be one of. Oh, get URL. Oh, I think I've mistyped. I think that's what I've done. Where did I put it? Oh, look, I've got a capital R. This is what you get through. And it worked. Okay, so it was just a key was there. So that's now running, and so then if we we can still curl our local machines, not doing anything special. If we ask for Google, that will have triggered our canary, and now all we're now waiting for is the speed. Oh no, look, I've now got an email. It tells me my canary was triggered, and if I open it, it will tell me my canary was triggered. The reminder, it's a canary. Ignore my IP address. That's the wrong end of a VPN, so it's not going to help anyone. But it tells you like the user agent, which was Go, and a canary token ID, which can be used for other stuff. So
and the timestamp is basically now or this minute, because it says 13:27, but that's in UTC, and we're in British summertime, so my clock says 14:27. But yeah, that's.
Oh yeah, and this computer is probably out. Yeah, I'll set the clock. I meant to set the clock correctly before we ran it, but yes, but certainly this is triggered. I mean,
yeah, no, I think that is correct.
Yeah, because this will be the time that it hits canary tokens.
Yeah,
so these times will be correct. My local ones will be skewed. But yeah, so there you go, canary token hit, which is quite nice. So that's canary tokens.
So that could be one. I guess it's a different form of getting alerts. You can almost like, it reminds me of if this then that. That you can have Tetragon trigger a canary token that lands in your email.
Exactly. So the way I like to talk about it is if you have a vast volume of data that you're recording in your SIEM or your data lake or wherever you're putting it, because you might want it for future investigations. You don't know what you're going to need, so you capture as much as you can, and you've got the money and the bandwidth to store that. Great, right? But what if something really big happens? You don't necessarily want to have to wait for your pipeline on your SIEM to kind of run and trigger, which you could do, obviously. Instead, you can do this. So John Fasterbend, my manager, really likes it because it's basically 1 million lines of code to get something that happened in the kernel into something in your email, which is kind of a mad sort of thing. But and it's going off for our third-party services to do so and all sorts. But you can have this trigger anywhere in the kernel, and so based on whatever arguments there are and decisions that you want to make. So it's very if then that, but in the kernel into your email, and if you use the whole thing's canary into your Slack or whatever. And you can have as many as you want. So, and they can all have their different reminders. So then you can use your email tool to filter the ones that are more important than the other ones, or however it makes most sense. It's an instant alert, which I find really cool and really handy. So
that's great. Yeah.
So yes, that was the second thing. The third one I want to talk about was match binaries. So this is something that's seen some attention recently. I improved string matching some time back. I think it was earlier this year, so that we could match on as many strings as you could possibly put into your policy, and we could have prefix matching, as many of those as you wanted, postfix matching, as many of those. So if you were matching strings in buffers, for example, or whatever, then there's a whole load of things you could do, which makes it, a much more usable tool than the kind of limited kind of approach that was put together before, which is mostly getting the concepts out there and seeing what people like, see what people use. Well, people like string matching, so we made that much better.
So you might use that string matching for like the parameter to a system. I guess a file name would be an obvious.
Exactly, yeah. file name parameter is the obvious one. But yeah, anything that takes a string. Theoretically, a buffer you read from the internet, you could match on. There's all sorts of things you could probably
executable names. Yeah.
Well, for executable names, you really want match binaries, because if you were matching on the string might not be the actual binary. The string that an attacker types in or someone types in might have like .. / / type redirects in it, which you'd have to kind of resolve.
Yeah.
It might go through symbolic links. You'd have to resolve those, etc. So, and there's race conditions as well. So there's all sorts of things. What you really want to do is you want to match on the actual binary.
Right.
So someone in our team, Mahay, put together match binaries based on my matching strings. So you could, I'll show you. Why not? Let's have a look at some things. So first of all, we'll kill Tetragon. Yep, I think so. Looks like it's shutting down. Hopefully it is. Yep. And then I've got, so we'll use the match bin example. So I've got a couple of cases. I'll talk to this policy. So this policy is just going to hook on TCP Connect. It's got the same selector as we had before. So I'm ignoring anything local. I'm only caring about things that are remote. But I'm also going to I'm going to match binaries. So we can use the in operator here and give it a list. So I've only got one item in the list, curl, but you could have any number of things in there. And if it matches on that, it's going to issue a kill. Okay. And then separately, we've got the same match block again, the same arguments here, but this time it's got match binaries, and it's looking at prefix of /temp, and again the same action of kill. So if you run curl and you connect to something remote, and it is then it will kill it. And equally, if you run anything from /temp that does a connect to something remote, it will also kill that. That's kind of what this is set up to do. And the obvious question, especially as we just talked about path names in things, is what is /user bin curl and what is /temp /representing? Like, is it the string? And it's not the string, it's the actual object on disk. So when your process executed, we store a representation of the actual path to the object that was executed as resolved, not the string that you typed with all the .. / and things like that.
So we could create, I don't know, a symbolic link that's something like, this is totally safe, but we link it to curl, and that's going to be matched because the fact that it's the execution.
Still going to catch it. Exactly.
Is that one, is curl.
Exactly. So let's do that, because that is the obvious test. So we quickly spin that up. Right. So if we curl to my local machine, not my local machine, my local network, it just runs, it does what it did before, because it doesn't match this policy here, because we're not matching. But if we curl to Google, hopefully my keys are visible on the screen. Yeah, it should be. Then killed in its tracks, so it works. So we could then make a link from user bin curl to this is totally safe, and we could run that to we'll go to localhost first, just to prove it's still curl and it still works. But if we went to Google, it's still being killed because it's resolved to the actual object on this, which is like really cool. The other one was, of course, if we took a copy of curl and we copied it into /temp and we called it safe, and we ran that one instead, yet again, it would work for the local one, but if we stick in the remote, it's killed, and that's because of the prefix here. So I'll talk very briefly how these things work, because it's kind of interesting. How do you match efficiently on a string, and how do you match efficiently on a prefix of a string? These are quite challenging things to do in the kernel. Like in user space, it's trivial. So if your tool captures everything and sends everything to user space, and then you filter, then this is just, for a high level language, this is like a trivial off the shelf thing to do. You know, is it that string? Of course it's that string. No, it's not that string. Is it the prefix? No, it's not the prefix. In the kernel, it's expensive. We don't really want to do a byte by byte matching. We don't really have loops. We kind of have loops on some versions of the kernel. We don't have them on all. Where we do have loops, we're kind of constrained in how we use them. Even so, everywhere we have a loop, it's costing us CPU cycles. And if this happens on every connect, it might not be too bad. But if it was every packet, you know, that sort of would mount up. So instead, of course, what we do is we use a hash, and we store all of our strings in a hash. And that sounds like the solution to everyone's dreams. But how long could that string be? Well, if it was a path, it could be 4,096 characters long. So do you have your hash key as being 4K and most of it being zeros for the vast majority of things you put in it? Well, probably not. You could do it based on the policy. Check the policy beforehand, find the maximum length of string, and then make that your key length. And then at least only some of it will be zeros for all of the different things you're matching. But what happens if you then add another policy? Well, you know, you've already created your table. You've already got your maps, you know, and now your map key needs to be bigger. Well, it needs to be different maps, so you can't really do that. You know, it prevent you. So you need to know ahead of time what's the maximum string you ever wanted to match, you know. And so you guess and you go, well, I don't know, 128 characters.
Most people probably it's only like 15 or something, but then for a lot of people it will be a lot bigger. Yeah.
Exactly. And if there's only one you need that's 128 characters long, but all those are 15, then all of the ones at 15, they've also got a massive key. So they're hashing a load of zeros that they don't need to be hashing. So the solution here, which you can see in the code, is what we have is we have a number of different sized key maps with different sized keys, and the different strings go into the different maps. So the amount of space you hash that's empty is minimal, because if your string is less than 24, I don't know, I can't remember what the limits are, 24 characters long, it goes into the first map, and the most you're hashing, you know, if you had a string that was 1 character long and 23 zeros, you're hashing 24 characters. It's not so bad. And then there'll be the next map will be like 48, the next one will be like another 24, the next one another 24. Why is it 24? Well, because the hash block size is 12 bytes, and so it wants to be a factor of that probably. And then also when you get beyond a certain size, you can just start doubling them, because once you get into big strings, we don't really care too much because we're already doing so much work. It just means that for the sake of having 11 maps that are kind of more sparse than having a single map, we can do every string from a single character to 4,096 characters, but we do it efficiently. So so it's kind of cool as it is. But it gets even cooler when you get to prefix, because obviously a normal hash doesn't solve the prefix problem really, I guess. It becomes I don't even know how you do that with a hash. You'd have to loop through and make your key incrementally bigger until it matched something, or it didn't match, or whatever. It'd be a tricky thing to do. But instead, we use the BPF LPM tree maps that are part of the kernel. So these are least prefix matches. They're designed for matching IP addresses and MAC addresses so that you can direct packets fast based on policies. And you're assuming a cider, and therefore you're matching from the start up to a certain point. Well, that sounds a lot like prefix matching for strings. So we abuse those maps, and we just stick all of our strings that you want to map like /temp/ into that map, and then we look up the binary that we're running, or wherever we run it, down here, and it finds the longest prefix in the map that matches. And so if there's no prefix in the map that matches, we have no match. But if there is a prefix in the map, it will tell us which one it is, and then we'll know which action we're part of as a result. So it's kind of cool that you can do prefix matching, and you can do that in it's not quite O1 like a hash, but it's very close to that. It's very like it's an algorithm that's been around forever to make routers and switches fast. So it's something quite quick. So that's kind of cool. But the reason I want to mention it really is because in this week, what day? Wednesday, I think it was, we merged a community contribution from Andre to do postfix in binaries. So we could change. Oh, I'm in the wrong one. We could change our policy, and instead of prefix, we could go postfix now. And instead of /temp/, maybe we just want to look for something that ends in curl. So we want to catch curl, but wherever it is on the disk. And so if we were to restart Tetragon with that policy, now we ran our thing from /temp, it's not, it's going to Google because it doesn't care. But if we had copied curl to /temp, not /tempo, that's a silly thing. I might quickly remove that because I'll never know what that is. But instead I've copied curl to /temp /curl, and if we were to now use that curl, it's now killing that based on it being curl, not on it being in /temp.
Nice.
So that's a really handy kind of addition, having a postfix match.
We've got a really great question came in from D. Do we have options to block anything based on its thumbprint? So I guess some kind of hash of the executable or something like that.
So file stuff is kind of not the side of the ship that I kind of concentrate on. I believe work has been done in that area. I believe in-house we certainly have work on Tetragon extensions and things that other the customers may well have, but I don't think in open source as yet we have matching based on hashes. It's not to say that we never will, but and obviously if someone in the community wanted to contribute that, I'm sure that would be a great addition. But yeah, I was going to say quickly how postfix matching works, because we use the same hash LPM tree hash type, except we reverse all of our strings when we put them in the table, and we reverse the binary that we're going to match on when we do the lookup, and then we get a postfix match the same way we've got prefix matching. So
That's super clever. Yeah.
Slightly more expensive because you've got to reverse the string, but it's still a lot cheaper than doing it another way. So that's kind of cool. So that was 3 things that you might not know about Tetragon, but there is a 4th that I can, if we have time, I can show.
Let's do it. We have time. Yes.
Okay. So this is something that I put in a while back, which is rate limiting. So because we observe everything in the kernel, we make our decisions in the kernel, we decide what action we're going to take in the kernel. When that action is to send events to user space, sometimes we don't need all of them. So for example, we've been talking about TCP connects. The nice thing with TCP is obviously it starts with a connect or an accept and it ends with a close. And so if you just report on the connects and accepts and the closes, you get a good picture about what's going on in the world of TCP. But with UDP, you don't really have that. You just have the datagram, right? So you could report every UDP datagram. And we have policies that do that, policies, I should say. But that's obviously a lot of data. So what you really want to do is you want to limit how often you report the same datagram. Mm-hmm. And so I introduced rate limiting mainly to do that. So what you could do is let's have a look and see what we've got available. The DNS or datagram with selectors. Oh yeah, I was going to. Okay, well I didn't demonstrate the DNS one, but we'll probably don't have time for that. But datagrams, right? Let's have a look at that. So because we're dealing with UDP, we're going to have the socket tracking because we need to, a lot of things that happen in UDP are going to be asynchronous, the things we care about. I don't know why we've got TCP Connect policy in there. We don't really need, but that's the policy we had before. But this one here, this will catch all of our datagrams. So for kernels older than 5.18, this will work. For 5.18 onwards, there's other examples in our examples directory. So in the open source repository for Tetragon, there's an examples directory, and in there's a tracing policy directory, and in there you'll find lots of tracing point policy examples. Have a look at the datagram ones. If you've got a kernel newer than 5.18, then there's different versions. But it's kind of simple to demonstrate it on an older kernel because we just have one hook instead of like 4. So this one sees every datagram, right? And index 1 is a SKB, which is a socket buffer, I think is technically what it's called, but to us it's a datagram, right? It's an actual packet. Actual index 0, which I'm not collecting here, is the actual socket, the actual sock.
Okay.
That it's, but because we can see the datagram actually probably gives us the kind of information we might want. And the second index is an integer, which is I think it's technically the type of thing that's happened, but 2 of those things are ingress and egress, which are mostly what we see. So we get like a 0 or 1, we pretty much know we're sending or receiving, which is why we kind of care about that one. And then we do our selectors, and we're going to match the protocol part of the SKB, index 1 to index 1. So that's SKB, so the protocol part with UDP, because we only want to see UDP datagrams, and we're going to have a limit. So our action is going to post, but we're going to rate limit that to 10. So that's 1 every 10 seconds. If you put an M on the end, it would be 1 every 10 minutes. I think you can have H for 1 every 10 hours. I don't think we went as far as days, but by the time we get to days, you can probably do that for 24 hours. Can you see? So there's various. It's all in the documentation. But now what we should see is 1 datagram per 10 seconds per tuple. The way it kind of works internally is it's for everything it reports that's got a rate limit option, it's going to store up to 40 bytes from every argument that you've listed. Why 40 bytes? Well, 40 bytes is an IPv6 tuple. So source address, the destination address, the source port, and the destination port adds up to 40 bytes. If you've only got IPv4, don't worry. The other bytes will be zeroed anyway. And if you're matching on strings, you can have up to 40 bytes for your rate limiting. And beyond that, it's probably not very efficient anyway. If you need rate limiting beyond that in the kernel, then come and talk to us. We might have other solutions. So that's what it's going to do. It's going to match these things. So if we were to run that policy, so we need to set the policy here to, what did we call that? Datagram with selectors. Right. And then we're going to match on this. In fact, we'll just match on that. So what I'll do is, I will follow the events. This is probably where it will. Yeah, let's just follow all the events. Who cares? I'm sure it'll be fine. So here's a load of events. I've not pretty printed them, but hopefully it will make sense. What we're going to need is a few more windows, isn't it? Okay, yeah, it's gonna be a struggle to demonstrate it on this window. It's the trouble. How can I do this quickly? I can quickly connect to a different window. Let's kill that. Let's get out of this. Let's go in here. Right. So if I was to run, right. So if what I do, if I was to run Tetragon and give it the same one, Datagram, right. Get that all running. Right, so now it's like picking windows and hoping they're all empty. So if we create some listeners, yeah. So we create a UDP listener on port 11,001. We'll create one on 11,002. If we use this window, we could. So we want to monitor it all somewhere. Maybe we'll monitor on this one. Right. Think about where it is. Live. This is all live, you know, all this kind of stuff. Right. So there's our events coming out. So if we were to now go to, I don't know, it's got like 9. We can netcat to the loop back on the first port we had and stick in loads of stuff like that, loads of datagrams, and we will have, hopefully, there's the datagram, but before that, nothing. So what we've caught is one being sent and one being received, and nothing since. And so I give it a bit of a gap. If we now send a load of more in, we can see we've got one sent and one received, right? Because we're seeing both ends of the connection.
Yeah.
Obviously, other stuff will occur. If we then were to go to once you end the second port, we have the second port. We send. Oh, what's that not running? That's weird. That's the wrong command. Obviously, that'll be why. Right. So that's listening. Go to the next one. Right. So if we do that, and now we can send loads of datagrams to that one, and we would see again similar thing. Lots of socket action going on, and then a send and a receive. But we should only be limiting each one for 10 seconds. So if we go back to the first one, send some datagrams, we get datagrams. We go back to the other one, send some datagrams. Oops.
Is it within 10 seconds or not?
Yeah, so then we're not. Yeah. But if we send some more, so the thing is, 10 might have been a bit like, right. So it's rate limiting one when it's not limiting the other. You might have to go back and watch the video again, frame by frame, to see exactly that. And if I had a better demo, I'd have done a better demo.
Great question here, though, from Darth Vikes. Rate limiting seems also like it could be pretty powerful if it can be more dynamic, say, against someone doing a DDoS against you.
Well, we're rate limiting the events coming in. So yeah, so if someone was doing something that was going to generate loads of events, and that was going to flood your user space or flood your SIEM or flood whatever, you could call that a DOS or a DDoS against Tetragon itself or against your logging kind of architecture.
Somebody is calling Elon as we speak. Yeah.
Yeah, exactly. It's clearly what they needed. Then rate limiting would help in that case as well. I mean, to make it dynamic, you could extend Tetragon to make it dynamic. You could extend Tetragon from outside of it by changing the policy on the fly as you detected the things you wanted to care about. But really, you're mostly just, the idea is to limit too many events that are saying the same thing, and every UDP datagram for the same tuple is mostly saying the same thing. Data happened. Now, if you care about the actual data, then obviously that's a different story. But if you're just caring about who's connecting to what, which is mostly what we care about, then that's really what it's kind of there for.
That makes sense. Another question from Darth is asking about security best practices like CIS. Could there be a list of standard, I'm going to say policies, that could be imported and used? I know of there's the white paper that folks at Isovalent, our colleagues at Isovalent, wrote along with some friends at Control Plane, and that talks about how you can use Tetragon policies to implement some of the, I can't remember whether it was NIST policy or NIST guidelines. Off the top of my head, I've blanked on exactly which guidelines it is, but maybe those FIPS compliance guidelines, I think. So yes, it is certainly possible to have some kind of pre-formed ideas about what kind of rules you'd have that could implement a particular policy or a set of best practices. I know the CIS ones a little bit I know about. They tend to be sort of application specific. I worked on some CIS guidelines for Kubernetes, and it was more based on configuration. So you'd have to think about how to write Tetragon policies that detected if the configuration was sort of set up in the wrong way. Like, what kind of event could you detect that indicates that that configuration is wrong? But I think the general principle of using Tetragon to implement those kind of policy guidelines, absolutely, yes.
Yeah, certainly. And it'd be a great thing to extend via the community. Really, would be to pull together to try and find good or handy kind of sets of rules that people might want to pick and choose from. In the world of Sysmon on Windows, from Sysinternals, there's a massive repository. So Swift on Security runs one. Oleg, I can't think of his saying off the top of my head, runs another one. And there's further ones beyond that. But it's basically community supported. It's just a GitHub repository, and people put in their own rules. And if you want those rules, you take them. If you don't, you don't.
Yeah, so, and you're already mentioning the example policies that exist in the Tetragon GitHub.
Exactly, and we're on Slack on the Tetragon channel on the eBPF and Cilium Slack. So if you have questions about them, or you want to turn those examples into something that does a specific thing, then obviously come and ask questions. We try and help as best we can.
Fantastic. So we're pretty much getting to the end of the hour. We covered not just 3, but 4 things that people might not have known about Tetragon. We talked about in-kernel selectors, so being able to filter events in kernel. We talked about canary tokens. We talked about binary matching with prefixes and exact matching, and also postfix matching, which is so cool because you just reverse the...
Yeah. Exactly, and it's cool because it came from the community. It's the most recent update, but it's quite a big one. It's quite a challenge to do. So.
Fabulous. And then finally, we've talked about rate limiting. So I think you've given us a really nice tour of some really cool features in Tetragon. So thanks for being with us today, Kev.
No worries. Hopefully people will make use of them.
And thanks to everyone who's been watching. Thank you for everyone's questions. I know there were 1 or 2 that we didn't really manage to squeeze in today, but hit us up in Slack and we will try and get those answers to you. The Cilium and eBPF Slack is where we all hang out. So fantastic. I hope everyone has a wonderful weekend. And with that, we'll say goodbye.
Bye-bye.